Morning to USA and very good evening to India. Warm greetings to all participants as explore the space in association with MATSI Innovations and UC Davis College of Engineering Material Science Department gets ready to launch the program Indo-U.S. Youth Space Talent. Dear participants, this is a very special program aimed and focusing on highlighting, identifying, and showcasing youth talent in space industry in both India and USA. We have a galaxy of great speakers and youth icons from United States of America who are going to make their presentations. The inaugural speech is by Dr. A. Kiran Kumar, former chairman ISRO. We have a recorded speech from Mr. Kiran Kumar. That's a great source of encouragement for us. And then we have special addresses from two very eminent gentlemen, Mr. Tim Dyer, Executive Director, Fralock Inc. USA, and President, MATSI Innovations. And along with Tim, we have Professor Subhash Risbut, Distinguished Professor Emeritus, Material Science and Engineering, UC Davis College of Engineering, USA. A special welcome to Tim and Professor Risbut. We have also other eminent people who are joining for this webinar. A special welcome to Dr. Jaydeep Mukherjee, scientist from NASA FSGC. Among the youth icons, we have Ms. Cassandra Brayfield, PhD scholar, UC Davis College of Engineering, and Mr. Kevin Yates, PhD scholar, again from UC Davis College of Engineering, who are going to make very interesting presentations today. Ladies and gentlemen, the objective of the program today, as I mentioned, is to identify and celebrate youth talent, especially in space industry in United States of America and in India. This particular program has identified two youth talents, Ms. Cassandra Brayfield and Mr. Kevin Yates. Let me run a very short presentation of mine, which will explain the theme of our program. Is my screen visible, please?
Yes.
Thank you. Thank you. Ladies and gentlemen, we all know that space exploration is a conglomeration of various technologies and ideas. As depicted in the slide, we have deep learning, data collection, Earth observation, rocket landing, new energy sources, space electronics, and many other very interesting technologies which make space exploration something that is driven by multiple disciplines. With that in mind, we have Ms. Cassandra Brayfield, who is going to speak on energy solutions, solar cells and alternative fuels. And then we have Mr. Kevin Yates, who is going to speak on the biotic future, human space exploration. These are some interesting citation, medal, and certificate, which will be presented to the two youth icons by Mr. Tim Dyer and Professor Risbot after this program at the campus of UC Davis. Many thanks to you, Mr. Tim Dyer and Professor Risbot, for having kindly agreed to give this presentation to the two youth icons. On the particular topic of today on Indo-U.S. space cooperation, we all know that NISAR, a joint venture Earth observing satellite between NASA and ISRO, is presently the highlight of Indo-U.S. space cooperation. NISAR is a satellite that's ready to be launched by ISRO in early 2024. NISAR is an Earth observation satellite which will observe a wide range of changes in the space spectrum. On the two markets, India and United States of America, ISRO has been and continues to be the leader as far as the Indian space industry is concerned. InSpace and NSIL are new entities that are formed to encourage private participation in the Indian space industry. As far as the United States of America is concerned, they have a much longer history of privatization. As this slide depicts, there are more than 5,000 space-focused companies in the United States of America, and there are over 400 private space companies in India. Ladies and gentlemen, on what this particular program will offer, this program at this point offers interesting and special programs on space industry in UC Davis. For anyone who is interested, they are welcome to get in touch with Explore the Space. We'll be more than happy to facilitate that. We are talking about internship opportunities in different cities in India and also in the US for participants in this program. Industry visits are planned. We are planning space industry delegations to USA. In particular, the Silicon Valley Space Industry Orientation and Space Tech Expo in May 2024, Long Beach, California, USA, are two very interesting programs that are going to offer a lot of linkages for the participants, which will bring the Indian and American space industry. We also have the online certificate course, STEM and Basics of Global Space Technology and Industry, with inputs on aerospace and defense. So, friends, these are at this point, this is what this program offers. But as I mentioned, this is going to be a 2-year program with youth icons in space industry being identified and celebrated in the campuses of universities both in India and in the United States of America. That was a very proud moment for Explore the Space when we were given the title as ISRO Registered Space Tutor. We have Dr. Kiran Kumar and Mr. Sudhir in the picture there. This was another proud moment when we had Mr. Somnath, chairman of ISRO, who visited our stall at Bangalore Space Expo in September 2022. Explore the Space, a fledgling firm, also visits the US market. There you see Explore the Space, visiting the Space Tech Expo conducted in Long Beach in May 2022. We have an interesting program called the Global Space Business Bulletin, which connects opportunities with capabilities across different markets with particular reference to the space industry. That's the online certificate course, which was launched in May. I'll have to say that it is really doing well in the India market, and we really hope to take this to the other markets. At this point of time, there is a very strong current. There is a very strong current encouraging us to focus on California. The title of the program is Indo-U.S. Youth Space Talent. But then, as the slide says, California is a global aerospace leader holding 9% of the combined global space. And then California generated close to 6 billion aerospace industry revenues, representing 9% of the global aerospace and 21% of the US industry. So California is really big. At this point of time, we are looking at California for more programs. We are very much aware of the great support that we have been receiving from other parts of the United States. Also, we acknowledge with gratitude the presence of Dr. Jaideep Mukherjee from Florida. So definitely there are other universities in other parts of United States of America where we want to take this program. But as I mentioned, at this point of time, we are looking at California. With this, my presentation comes to a close. So thank you, ladies and gentlemen. That's a short depiction of what Explore the Space has been doing all these years, and why and how we want to celebrate the youth talent in India and in USA, particularly in the space industry. Uh, Now, I have pleasure in reading a very short bio of Dr. Kiran Kumar, and as I request my colleague to play the speech, the inaugural speech of Dr. Kiran Kumar. Ladies and gentlemen, Dr. Kiran Kumar is a distinguished scientist and a former chairman of the Indian Space Agency, ISRO, a highly accomplished space scientist and engineer with a distinguished career spanning over 4 decades in ISRO in the satellite payload and application domains. He has made immense contributions to the design and development of electro-optical imaging sensors for airborne, low Earth orbit, and geostationary orbit satellites. Dr. Kiran Kumar has also made significant contributions for evolving the observation strategy encompassing land, ocean, atmospheric, and planetary studies. Now, I request my colleague to play the inaugural speech of Dr. Kiran Kumar.
Ladies and gentlemen, greetings to all of you. I am pleased to inaugurate this interesting series of Indo-U.S. Youth Space Talent, a series of programs planned in India and USA to promote further cooperation between India and USA in space education, research and industry. I am glad that an ISRO registered space tutor, Explore the Space, has joined hands with University of California, Davis, USA and MATSI Innovations, USA in doing this very interesting program. It is heartening to note that the partnership between India and USA is on a steady growth path as ties continue to expand between the two countries. Space industry collaboration in particular and economic and social benefits for both the countries that are going to happen because of such a cooperation are very promising and interesting to note. Science and technology cooperation between USA and India strengthens our bilateral relationship, promotes economic growth, and allows us to develop new and innovative technologies and products to address shared challenges. The United States and India believe that science, technology, and innovation are key tools that will help us address global challenges, which include climate change, health, education, food, water, and energy security. Both countries support cutting edge research and are building public private partnerships that promote science and technology based in innovation and entrepreneurship. The United States and India also recognize the importance of gender equality in scientific workforce and have conducted numerous exchanges to encourage increased participation of women and girls in science. The two countries have taken significant steps in advancing the private sector. The endeavors will shape the impact US and Indian space policies and programs over the next decade. Recently, India and US have agreed on advanced space collaboration and cooperation in several areas under the Initiatives on Critical and Emerging Technologies umbrella. And this comes at a crucial time for both countries. This follows from the meeting of the US-India Civil Space Joint Working Group, which was held in January 2023. The solutions to induce long-term cooperation is to sustain engagement between academics, private sector, and state-led entities in the two countries. It could also take the form of collaborating on highly specialized projects such as NASA ISRO Synthetic Aperture Radar mission. India and USA are adopting many novel approaches in new space age to achieve a very significant and meaningful partnership. More Indian students travel to USA and back and forth with ease, and this is something that needs encouragement. India and USA are also working on a very advanced NASA ISRO synthetic aperture radar mission which enables measurements and the causes of consequences of land surface changes using advanced radar imaging. This mission concept and the resulting partnership are in response to National Academy of Sciences 2007 Survey of Earth Observational Priorities for the next decade, known as the Decadal Survey. One of the top priorities identified in this survey was to gain data and insight in three earth sciences domain: ecosystems, deformation of Earth's crust, cryospheric sciences. This initiative to encourage and identify youth talent in space technology arena is a very commendable one. Tomorrow's prosperity and peace depends on how we cultivate the youth of today. I congratulate the organizers for this initiative and wish them a great success in their endeavor to enable the next generation to appreciate the rapid progress that is happening in the arena of space and how this can be used for both sustainable and progress of humanity, not only on planet Earth, but also in its exploration of the universe. Wish you great success. Thank you very much.
Thank you very much, Dr. Kiran Kumar, sir. That was a very inspiring inaugural address that should take us through the entire series. This will be the inaugural address for all the programs that we plan in the series. As very well said by Dr. Kiran Kumar, the way that we cultivate and encourage the youth of today, so much depends on how our tomorrow is going to be. So thank you again, Dr. Kiran Kumar. With these words, I have pleasure in requesting our great friend, Mr. Tim Dyer, Executive Director, Trilog Inc. USA, a ceramic leader, and President, Maxi Innovations LLC, for his special address. A few words about Tim. Tim is a material scientist and a senior executive in leadership position with 25 plus years experience working as process engineer, ceramist, senior engineering director, Vice President Operations, Chief Technology Officer, and President for startup to medium-sized public and private companies. With a bachelor's and master's in material science and engineering from the University of California, Davis, creating and making products at nexus of energy, fabrication, technologies, and material science is the special feature of the distinguished career of Tim. Over to you, Tim.
Thank you, DV. Welcome all. Thank you for inviting me for this talk. And I always have to commend DV on his mission to promote engineering and math education to everyone, a diverse population of young people, women, men, everyone around the world. It's important that we all contribute to improving our plight as mankind by seeking academics and also using space as a way to bring people together. So I don't know, DV, if you want to bring my slides up, it'd be great to do that.
Yeah. Yes, Tim, your presentation is going to be played now shortly. Yeah, getting ready.
Yes. Thanks, DV. This presentation is my journey as a space enthusiast. We're all space enthusiasts, or maybe we become space enthusiasts when we're young. But everyone has their own journey, and this is just a story of my journey. So then, I think the next slide, DV. And you could put it in slide presentation mode. It might be bigger. if you want to do that. Anyway, this is my story. Is I was born in California, and I'm a half German, so I'm son of a German immigrant. And then I decided to become a material scientist in 1989, and I was inspired by a professor at a junior college to do that. I have both a bachelor's and master's degrees from UC Davis. I have my own company, Mad Sci Innovations, which allows me to work with companies helping support ceramics solutions. And then in my spare time, I like mountain biking, yoga, traveling, and making bad wine. And also, I was inspired to become in this hobby because I liked to build rockets as a young child. I was very interested in mechanics and definitely energy. TV, get the next slide. Part of my participation in promotion of the whole explorer space is based on my passion, and that's to really help create solutions that allow us to store energy, convert energy, and manufacture devices that really help us advance as a civilization. And then this gives us definitely benefits in terms of space products. I like to enable green energy startups to make fossil fuels obsolete by 2035. I think that's definitely hydrogen, lithium-ion batteries, and solar and renewables will help that. I support a lot of startups with that because they don't have the money to have large staffs of engineers. So it's good to participate and help them as a consultant. I also like to achieve results with people. So I'm a good team leader and project leader and coach to actually help companies achieve the results. And in the end, the whole idea is to help the people that are customers or the technology development companies to get their products to market faster. That benefits mankind. And also the way technology works is the more technology you have, the faster it develops. It's an exponential relationship of time. So it's not linear. Tech kind of builds on itself almost like an avalanche. So we really want to accelerate tech to get us to the next level of technology faster, which could enable even greater things and safer flight. You go next slide, Evie. Bless you. The next slide. All right. This is just my journey. So everyone has a journey and their way of getting into the space industry. So let's see, my timeline in 1967, 1979, I was a child and I had a twin brother, and my dad used to explain it, read books about the space, and we would actually use an optical telescope. We'd go outside in the backyard, and I would be able to see Mars and Jupiter's and the surface of the moon. This was a big impact on me as a child to kind of see that space is real, but really my dad really helped bring me along. I learned how to read star maps as a young, and then understand where Polaris were and the constellations. And then as a young child, I also developed water rockets. I mean, you could buy these that made out of maybe like a 2-liter bottle, or it could be a 1-liter bottle of soda. You could buy these kits that you just use an air pump, like a bike pump, and you can pump it up and launch rockets. These are very easy to make and are pretty safe. And later on, we went to solid rocket fuel rockets, more of the traditional rockets that you see from hobby stores. They're a little more expensive. We also watched a lot of TV at the time, which related with Star Trek and other space shows that helped us inspire me as a space hobbyist. And so the next slide is kind of shows you, DV, next slide, show kind of some of these devices that I think are necessary, at least for my development. The star maps, of course, understanding those as a child. Telescopes are a great way. You can see space, inspire yourself. Water rockets, you can see on the right, that's very easy to make. They're good, fun, and definitely you can share this with younger people if you want to help them, inspire them. And then the solid rocket, the Big Bertha is an example of a solid rocket system that you could buy. And again, these are nice ways to get people excited about space, but also to help excite me. Next slide, DV. There wasn't the internet in the 70s. So how we got to see in the 80s, we got to see space was really through TV shows. Now there's such a wealth of information that you can get, which is really just amazing, where we didn't have that in the past. So we had Space 1999 and Star Trek and Star Wars. These really were the things that showed us what space travel could be like. because we didn't have this information other than going to the library and checking books out, or you had to actually go to microfiche to read things. So it was not as easy to get information as you do now. So we have a great benefit that with the internet and Zoom and all these resources that we can learn faster. But in my days, it was done via TV shows. So next TV. Next slide, yeah. In the 1980s, it's really when I was in high school. I did really well in high school and focused on music, physics, math, and chemistry. And these are things that help build the space, again, the space skill set, material skill set. Traveled with my family to space museums. And I know that all over the world, they have these museums where you can see it. I also learned how to program computers and save my money to buy Atari 800 XL. That really helps you understand because computers and controls are key to space technology and also key to a lot of engineering projects. You got to know how to do that. I learned how to program calculators to solve problems, even cheat on exams occasionally because you could actually make the calculators pretty advanced before the professors figure that out. And my twin brother and I, we built a lot of, like say, funky devices, including, we did a lot of works with air-cooled motors, with Volkswagens, created odd inventions like cannons and rocket engines. So we're always playing around with stuff because it's really, it's building things and trying it again and again, and also good characteristics of people who want to get into the space industry that you really have to be tenacious. You can't easily quit. And then we watched the shuttle Challenger mission failure in 1986, which is a big impact on me because that it really shows you how you really have to be careful in terms of space. And also it was a material science issue that caused the failure, which Professor Feynman determined, which was a O-ring glass transition temperature problem, which kind of pushed me into the material science field, seeing that it's important that the materials that you use are key to success of missions. The next slide. And then here's examples of going to the Boston Space Museum and then old computers like before internet, Atari 800, and then an air-cooled Volkswagen motor. You might still have those in India. I don't, maybe you have those found in other countries. They're definitely in Mexico. And here's a tennis ball cannon, which I don't recommend you construct, but they're very fun in terms of what they could do. Next slide. 1990s is really when I developed my college career. So some people go directly to university. In California, you can actually go to junior colleges, and they're phenomenal. And that's where I really was inspired to become a material scientist. I started as a mechanical engineering student there and actually worked through school. So my parents didn't have much money, so I self-supported myself. In those days, you could get away with that and put in selling auto parts and repairing cars. I transferred to UC Davis for my junior year, and it was a great getting into UC Davis. Exciting, it was a big college, and that's really where I became totally a material scientist. I went from mechanical engineering to really really love ecam. And I continued on at UC Davis to get my master's degree in materials engineering, which I recommend that most people do because really the bachelor's is like getting a taste of something, and a master's degree is actually baking something, like learning how to make cakes and then making a cake. Master's degree does that. And at UC Davis, I got to do a lot of stuff, like build some evaporator, electron beam evaporator. I had exothermic films. I built furnace to grow germanium crystals for chemical engineering. That was Paul Zaglu, Professor Paul Zaglu, and then learned how to machine my own components out of aluminum stainless steel. But made CNC, and Davis has a wonderful innovation center now that has all this capabilities to do the machining. So they have that, but I actually had to go to Walker Hall to do that when I was at UC Davis. And I actually worked on the ESCA machine at UC Davis, which I'm not sure if it exists anymore, but I actually worked that for Professor Munir. And finally in 1992, I got right out of UC Davis. I became an employee of Applied Materials, a big company that makes semiconductor manufacturing equipment. Next slide. So next, yeah, this is just an example, a visual of my 90s, where I went to Santa Rosa Junior College to get my associate's degree or whatever. Moved on to UC Davis to get my bachelor's and master's degree in material science and engineering. And then went to Applied Materials and developed this particular product, which is a high density plasma chemical vapor deposition system used for making chips kind of in the 0.13 micron, 0.12 micron design node, which is kind of old school, but again, at the time it was state of the art. Next slide. From then on, I worked in the semiconductor industry for 10 years, making semiconductor fabrication machines. And I made the full dive into ceramics by moving to Morgan Ceramics in Auburn, California, and eventually Hayward. After that, I built ceramic factory and pumps for large seawater desalination plants, Perth, Australia, Israel, Spain, Caribbean, Mexico, Cabo, giant pumps for seawater desalination. It really reduced the energy by 60%. And then I went on to develop machines that enable high energy density silicon anode lithium-ion batteries, and then revived Elcon Precision, LLC, by focusing on space and medical industries. So this is where I took my material science and ceramics background and applied it to actually bringing a company into space and medical industries. And so Elcon actually played a key role in the NASA DART mission. That was a global space defense project to demonstrate that we could protect our planet from an asteroid impact. So by deflecting Didymos Prime, it demonstrated that the DART, or the idea of using some sort of rocket ship or craft to deflect an oncoming asteroid is possible. Through all of this, my daughter Claire, she's really important to me. I taught her about space and the stars, and she actually watched the NASA DART impact and was really impressed by it. Dad's team was part of that. And now I'm building an advanced global ceramics company for Freylock Incorporated, which is a private equity company in California. And I have 3 facilities I'm working with in San Diego, Fremont, and also in Rockland, California. Next slide. So this is not a technical talk, but it's kind of a space enthusiast recipe that I'm sharing with you, is that what things that we have in common as space enthusiasts. You have curiosity, imagination, resources, willingness to learn, have a knack for space and science, willing to work hard, and a person to share your passion with. And then also you have a lot of information out there to learn. So these are all things that we have in common. So again, it doesn't have to be super academic. This is all a part of coming onto the space journey. And I really appreciate the opportunity to speak here at DV. Thank you so much. And I wish you great success in your program.
Thank you. Thank you so much. Thank you so much, Tim. Thank you very much.
Welcome.
Dear participants, I request all of you to turn your mic to the off mode, please. We are arranging this program with a great deal of effort being put in. I would request all the participants to turn their mic off, and then we would request the designated specific speaker to speak, and I kindly request all other participants to turn their mic off, please. Thank you so much, Tim. Dear participants, I would urge you to have a look at the last slide of Tim, where Tim lays a special emphasis on curiosity. So I think it's that curiosity which would drive anybody forward who is interested in space sciences. Thank you so much, Tim, for all the encouragement all these years. Ladies and gentlemen, I have pleasure in presenting to you Professor Subhash Risbud. Professor Subhash Risbud wears many hats, and only one of which involves his academic responsibilities in the University of California, Davis Department of Chemical Engineering and Material Science. He is also the director of the Campus Internship and Career Center. And very interesting is Professor Subhash Risbud is a devoted cultural ambassador for the Indian classical music. And Professor Risbud takes very interesting special classes on music. That's very interesting to know, Professor Risbud. Now, we would request Professor Risbud for his presentation, please. Over to you, Professor Risbud.
Yeah, well, thank you, DV. If you would put on my PowerPoints, I appreciate it very much. And I'll take this opportunity to start, while you're doing that, to thank Tim for an excellent presentation and being an ambassador for UC Davis in a variety of ways he described. I'm very much a friend of Tim's, and he's been collaborating with us on the senior design course for a number of years. and in many other ways as well. So his accomplishments speak highly of our alums from UC Davis. So let me start with my presentation. If you would project my PowerPoint, please. All right. Well, let me give you a quick history, as is the case. This is a talk that I'm very happy to be at and to be invited to. So thank you, DV, and all the organizers for taking the trouble to do this. Can I move on to my first slide right after this? The next one. So a quick history of where I have been. I was born on 3rd August 1947 in pre-independence India. So 12 days after I was born, the British left and India became independent. So that's kind of a high point of my birth time. And then I attended the Delhi Public School in Delhi, and then went on to do a BTech in metallurgy at IIT Bombay, now called Mumbai, and a 5-year program from 64 to 69, and then landed in Berkeley at an absolutely fantastic time in 1969, when Berkeley was the centerpiece of the free speech movement. So I saw and got educated in a lot of aspects at Berkeley in my early days here, and got a degree in ceramics with Dick Fulrath, who's a famous ceramic scientist at Berkeley, the late Professor Fulrath. And then I decided I wanted to go to work and get some experience, and became a crystal grower at Stanford Center for Materials Research for a couple of years, and then worked for a little while at a company that Tim knows very well, the old Wesco, Western Gold and Platinum, then later becoming GTE Sylvania, where we were doing alumina, ceramic substrates, so forth. And then I returned to Berkeley to get a PhD and finish it, and then have been in academic life ever since, until 2023, which is this year, earlier when I retired and became Professor Emeritus, and I still have a research program and labs. And Cassie, of course, is a great example of one of the many PhD students that I have mentored over the years. So academic life has been in many engineering departments, because right after I finished my degree at Berkeley, I went to the University of Nebraska in Lincoln, where they had a mechanical engineering department, and then moved on to Lehigh in Pennsylvania for the Department of Metallurgy and Material Science there, and then to the Ceramic Engineering Department at Illinois. And then I worked in the Optical Sciences Center at the University of Arizona in Tucson, and ended up at UC Davis in 1990, which is now 33 years ago. I still collaborate with people at Stanford, at LBL, Livermore, SLAC, and many of the national labs nearby. So that's been kind of my travel through various places. On to the next slide, please. Okay, here we go. I don't know what the green lines are, but anyway, so the goal of anything that we do, as Tim has pointed out, as DV has said repeatedly, is the first and foremost. I'm hearing all kinds of voices now.
Can I request all the participants there? I'm able to hear the voice of a child. Can I request the mic to be turned off, please? I'm sorry about this, Professor.
Oh, not a problem.
Over to you, Professor Isbut.
Okay, so as I mentioned, and then Tim has mentioned as well, the goal that we have all got is to encourage student collaboration. In a simple word, provide opportunities for students at all levels. And I emphasize that, all levels meaning undergrads, even high school sometimes. There are programs at UC Davis that have high school, undergrads, freshmen, sophomores, seniors, graduate students, postdocs, across the board. And so we need people of all backgrounds to come here and to collaborate with us on engineering, science, writing, communication, and so forth. So, that would be wonderful if students went back and forth from the United States to India and India to here and we get into a collaborative sort of environment, which I would very much like to encourage and which I've experienced most of my life. On to the next slide, please. Yeah. Okay, so a quick history of the UC Davis campus. It was founded way back in 1905 and mostly as an agriculture place because we had over 5,000 acres of land in the campus, and it was actually an extension of Berkeley in the early days, and because the ag people were heavily involved in growing everything from strawberries to other products. And then now currently, of course, which is this year, the UC campus has over 40,000 students and 8 colleges, which is a pretty broad coverage, and over 250,000 alumni that have gone on to do brilliant things. I mean, Tim being a good example. And then location-wise, for those of you that are not aware of where we are, because a lot of people know Silicon Valley and San Francisco, but we are located 10 miles or so from Sacramento, which is the state's capital, and 2 hours from Silicon Valley. So it's a relatively short drive to Silicon Valley, and we are in a rural agricultural sort of environment at UC Davis. The next slide. The College of Engineering was founded in 1962, sort of an adjunct to the agriculture department. So there was a lot of emphasis on food science and technology and plants and agriculture and all of those. But now it has grown to have many departments even within the College of Engineering. When I first came here, we were a part of a mechanical aeronautical materials engineering department called MAME, M-A-M-E. And that's where I came in at 1990. We were sort of a materials group of 4 or 5 or 6 faculty in a huge department of aeronautical, mechanical, and materials engineering. But double majors became a natural tendency because of that, because all of us, as many of us have pointed out before, we always saw in our department. So that became a very natural range of research and teaching.
Can I request that particular person to turn off the mic, please?
Yeah, somebody has their mic on.
Yes, please. Sorry
Okay,
about that,
okay, no
Professor.
problem. Yeah. Next slide. Okay, in terms of research facilities, I mean, over the years that the department has grown and the campus has grown, we have developed excellent research facilities for both materials synthesis, processing, making advanced materials. We've formed a central unit called AMCAT, which is characterization and testing. We've got great collaborations with mechanical, aeronautical, chemical, electrical, and several departments in engineering, even physics, chemistry. Students routinely go across campus to collaborate. So when anyone comes here as an undergrad or a grad student, it's almost a given that they will collaborate in many different areas, and not only the engineering college, but across the campus. Next slide. We have basically degree programs that I want to emphasize because we have now very recently, in fact, started this integrated 5-year bachelor's master's program. So if an undergrad is interested in a joint BS-MS program, and believe it or not, we have many undergraduates from India right now at UC Davis in the College of Engineering that I have taught as recently as last fall in my introductory material science course, who are here for a 4-year education, which they can convert in 5 years to an MS degree, a BS-MS program that does not require a thesis. So that's one excellent new program. We, of course, have the traditional master's degree with a thesis, which takes about 2 to 3 years. And then we've also very much interested in what they call a Master of Engineering program, which is a 1-year coursework only degree, which a lot of people that work or want to work in industry are quite interested in, which does not require a long thesis, but is still rigorous in terms of coursework. And it is quite interdisciplinary. And then, of course, the PhD, which takes 4 to 5 years beyond a bachelor's degree. So those are some of the degrees which are offered in our college and in our department. Next slide. One of the features that I want to emphasize that for a long time that I've been here, and I've been the director of our internship center, so I kind of know this much more. We have a long history of collaborations with just research and other things with national labs, which are nearby us. You know, Lawrence Berkeley Lab is less than an hour drive. Lawrence Livermore Lab, similarly close by. Stanford Linear Accelerator Center, Oak Ridge, Los Alamos. So in the past, people have collaborated with many projects. In fact, grad students many times who are doing a PhD, finish their coursework at Davis, and then spend the next 2 years at Livermore or Berkeley or someplace like that to finish their project and their research in those facilities, because they have some very good advanced characterization and synthesis and processing facilities. So we take advantage of all of those ties to both industry and national labs, industry being, you know, all the Silicon Valley, of course, rich source of industrial interactions as well. And I forgot to mention Idaho National Lab is another collaborator that we've had for a number of years. Next one, next slide, please. So what kind of education do I visualize? I mean, this is not new to anyone. When we say multidisciplinary projects are a constant theme in engineering. And Tim pointed this out earlier. We heard this repeatedly, that engineers must no longer only look at their discipline as the only education they get, because even during their education, they must learn the language and customs and techniques which are beyond their own field of study. I've had a wonderful graduate student, Christine Gulbrandsen, who did a master's, a PhD in material science while doing an MBA at the same time. So, you know, it's one of the best choices that she made for herself, because she wanted to be an entrepreneur, and she is right now a venture person in the Bay Area. So these are the kind of examples that certainly come to mind when I think of different fields of study. So you can combine a business or other kind of interest inside your science and engineering field. So this is the kind of education that's becoming more and more important as the future approaches us. Next slide. I'll give you some quick examples of the kind of thing we've been doing in more recent times in my research group. And one of the more fascinating things when I think of space, because there's so much emphasis on finding water in the universe somewhere, which we read about in the popular press. So we were doing a DOE-sponsored project for a number of years on freezing of water in confined spaces. So water, when it freezes in Lake Tahoe, of course, is a different kind of freezing. But if you confine water in small cavities of ceramics, for example, how does water behave? Does it confine itself to nucleating from the surfaces or from inside? And we did some study with silica samples, SiO2 samples, and found some very interesting freezing dynamics that suggested that when water freezes, it could have two different places. Voice again. Okay. The next area that I have a lot of interest in for a number of years, and a lot of us in our department in material science do, is spark plasma sintering, which is a technique that many of you probably heard about, where you take a powder of any material, composite or ceramic or metal, and can get it to densify from essentially very poor initial density, none. I mean, you don't need to do any previous densification, just put the powder in a dye that I've shown you in this in this picture here, a graphite dye, and then it becomes a solid disc, very nearly 100% dense in a matter of minutes, which is extremely rapid if you think of how much longer normal ceramic sintering takes, you know, which is usually hours at the very least. So this is a tremendous advance, and more of this is happening. People are changing SPS to fast and other techniques of sintering, which allow powder to disc transformation of the material in a very, very short time. Just two quick examples of what I've mentioned here in my group. And of course, there are other examples that Cassie will talk about in the context of energy and so forth. Last couple of slides, one more, next one. Okay, so what have I learned over the years about mentoring? I mean, in the last 50 years of my exposure to academia, I've mentored somewhere near 55 PhD students and well over 100 masters, and of course, numerous undergraduates who have worked in my lab and continue to work in my lab now. So one of the things I've really learned is to encourage teamwork. People have to work together in teams. And I think this has been told to people time and time again, that you have to work in a collective team environment. And more important than that, I really like to think that people should be encouraged, students especially should be encouraged at the very beginning to think independently for themselves and follow their passion. Tim gave a classic example of how he followed his passion and so forth. And I think that's something that sometimes is missing, because we tend to try to using the student as a lab assistant is not the right approach. And I've never taken that approach. I always want to think of my students as my equals who will become my colleagues and friends in the future. And that should start from day one in every situation that I've learned from my mentoring. And most important, build respect for everybody that they're working with, because your colleague might be the person you'll work for one day or work with one day. So, that's the kind of environment I would like. So one of the things I do in mentoring, almost unconsciously but deliberately, I want to show in the next slide, which is coming up, the last one. I always like to mix. Can I move to the next slide, please? The last one. Yeah. Here's an example that I've randomly picked out of one picture from my research lab. This is one of the corners of my lab. And the reason I'm showing you this, that there are three people here that you see in the picture, and they're pouring out of an aluminum oxide crucible a molten sodium-based silicate glass of some sort, a melt. But David Duval in the middle is a postdoc. April is a graduate student. And Shep Chan is an undergraduate. At the time this picture was taken, I think he was a sophomore, second-year student. But when all three of them work together to do this, he's helping, he's pouring, he's holding. This is the kind of example. Oh, I got unmuted for some reason. Okay. Oh, I'm hearing somebody talk. Okay. All right, well, I've finished with that. And so I just wanted to show you this sort of visual example to close, to say that collaborative research involves postdocs, grad students, undergraduates, and high schools even, to come together and work together and build a team. I'll close with that. And thank you again, DB, for giving me this opportunity. I appreciate it. And I hope I'll be able to answer any question anyone has. Thanks.
Thank you. Thank you so much, Professor Risboot. I remember many people saying that space education, we will have to take different kinds of people for space education. Perhaps some of the participants in this webinar remind us that we'll have to really take different kinds of people for space education. That's on a lighter note, but I apologize for the disturbances. Two things from Professor Risboot's presentation. When you said that education in the coming days is going to be really multidisciplinary, we cannot agree more on that. It is really true. And on the 2-year and 4-year courses, Professor Risboot, I like to say that there is a lot of interest in, let's say, there's a lot of interest in a 5-week course where startups, entrepreneurs would like to come to different parts of the US, to different US universities. In this particular case, UC Davis, to do a particular refresher course Here, it would mean something that is related to space industry, and we would definitely like to discuss the possibilities of such tailor-made short courses that would vary from 3 to 5 weeks. Would you like to
Absolutely.
comment on that, Professor Rispo?
Sure. Yeah. I think we'd love to develop that kind of a dimension. Yeah, absolutely. Yeah.
Thank you. Thank you so much, Professor Risbut. We will take questions at the end. Ladies and gentlemen, we come to a very, very interesting part of today's program. I have pleasure in introducing Ms. Kesundra Brayfield, a PhD candidate of material science and engineering at the University of California, Davis. Cassie's career includes a bachelor's from Rensselaer Polytechnic Institute, master's work at Arizona State University, and industry roles in startups like smart lighting and battery energy storage systems technology. He is currently working on a variety of energy harvesting and storage projects, including synthesizing iron-based catalysts for the production of alternative fuels and depositing and tuning the absorber layer for photovoltaics and solar cells. Over to you, Cassie.
Hello, thank you so much. Real quick, I wanted to ask DV, are we planning on running over, or should I kind of shorten my
15 to 20 minutes, we are fine with that. 15 to 20 minutes.
Sure. Excellent. Okay. So, I do a lot of science with energy, and I know that this talk is for Explore the Space, so I tried to take my work and kind of show how it can be expanded on for space use, space applications. And so I wanted to talk about fuel here at the beginning. We're kind of at a weird point in fuel technology because we're looking for greener ways to not use our fossil fuels and, you know, in that way, get rid of some of the pollution that is causing issues. And so it's tricky because the way that we are dealing with energy now is not good for the environment, but it's also not cheap enough to have widespread yet. And essentially, the problem that we're looking at is all of these companies, Toyota, BMW, Hyundai, they all already have prototypes that run on hydrogen, but we don't have the hydrogen fueling stations out on the road. And so we can't get those fueling stations until there's cars on the road, and we can't put cars on the road until we have enough fueling stations. And so we're kind of stuck. And the solution is to make hydrogen production cheaper. And so this can then relate back to space travel. As you can see, this is actually from the NASA website, a diagram of their engines there. And so you have a fuel and you have an oxidizer. And you can see here how there's this entire liquid hydrogen area in the fuel tank for these spaceships, that if using these methods, we need to get hydrogen for those purposes as well. And so in order to make hydrogen production cheaper, which will make it easier for everyone to use, we're going to be using a catalyst, which then decreases the amount of energy that you need to produce the hydrogen. And so specifically, I worked on two different alternative fuels. One is hydrogen, and the other is a liquid fuel called formate, which actually can be used in internal combustion. And so what we see here is basically the dream of renewable energy, where we can use renewable sources such as solar and wind to produce a fuel, which we will then combust for vehicles, everything from, you know, aerospace to automotive, any kind of combustion energy, and then recapture the carbon dioxide to make more fuel. And if that was possible, then we would be really far ahead with turning this environmental issue around. So I synthesized these catalysts, and I'll show you how it works. So these two images on the left are showing how in the lab we are creating these chemicals. And then these two images on the right are showing how by running these catalysts, which makes this liquid black, which you can see, by mixing it together, we are, yes, thank you. We are able to produce either hydrogen or formate, and the hydrogen setup is in a solvent and it's a organic acid. And so we're basically taking the hydrogen off of the acid and then releasing it as a gas. And all the way over on the right, this is a system that produces formate. The atmosphere inside the glass bubble here is actually carbon dioxide. So in an atmosphere with only CO2, we can produce a fuel using the catalyst, which is very, very cool. And so using these catalysts, it's much, much easier and cheaper to produce the hydrogen than the current processes we have today. And we're not releasing carbon dioxide, carbon monoxide, greenhouse gases. And we're actually getting, with the catalysts, a higher Faradaic efficiency. So you can see my numbers here. Commercial electrolyzers put out about 15 kilowatt hours for every 1 gram of hydrogen, and our catalyst was able to get 33, which is less energy required for more hydrogen produced. Hopefully, this kind of technology can then assist with cheaper fuels, greener fuels, and a better environment in general. So that, and then also on the other side, yes, capturing CO2. And just another really quick extension of this kind of work is there are these lovely biologists, chemists, biological scientists who are using the same process to capture CO2 to make that formate fuel, and they're adding an E. coli, and the E. coli can actually then be able to produce these molecules that can then be transformed into ethanol or ethylene, essentially a bioproduced, biodegradable plastic, which is very, very, very cool. Can we clear some of the drawings here? Can we turn off ability to color? Thank you. So this whole process has been describing the storage of the energy as a fuel, which we can then burn to get that energy back or react to get the energy back later. But what about harvesting the energy? There's ways to capture the sunlight using solar cells to produce energy. This is kind of harvesting energy from the sun, which we can then store in batteries or other storage forms. And so this is a solar cell, and this is how it works. The photons from the sun interact with the absorber layer of the solar cell, which produces electricity in the form of these electrons. And then we can use contacts, metal contacts, to carry that electricity to use for energy, like lighting this light bulb here in this diagram. So here's kind of how, very, very close up, there's this depletion zone. So basically we have one side that's positive and one side that's negative. And when that photon gets in, forces an electron out, which we can then harness as electricity. And then, oops. In some of this work, I just wanted to show this because it's very cool. There are ways to build molecules using virtual reality, which was me to model my material that I was then going to use for producing solar cells. And over here, there's an image of a theoretical setup that is a solar cell connected to a battery. It's like a one-stop shop for harvesting and then storing that energy. So that was very, very cool. And I feel very lucky that I got to work with VR so much like this. So the absorber layer is what I was really working on, which is the functional layer of the solar cell. So producing the layer that literally is transforming the photon into the electron. It's transforming the sunlight into electricity. And so there's a lot of people who are working on making that absorber better, less sunlight per energy or more energy per coming in. And so there's all sorts of engineering and processing going into creating these architectures. And it includes this patterning of the layers and nanostructures, what can give us the best performance. And if we go back here, you see this image on the left with these needles. You basically, this is a good looking absorber layer because you want to be able to see the light go in between the needles and then bounce around in between the needles so that we're getting the most interaction with the sunlight possible. And so moving from there, knowing all of that, we're working on the solar panels that can then be used in all sorts of locations. So we see these men on the roof putting them in on Earth, but then we can also see when we decide to move more to Mars and kind of terraform using solar cells. I mean, as long as the sun is reaching there or other star energy is reaching that far, we can harness it for energy. And so it's an intergalactic usage of these cells. And so we saw those needles from earlier, and I just wanted to show this here that I was able to grow something a little different than needles. And I have two different textures here. And if you look all the way on the left, these kind of black films is what it looks like when you're just looking at it with your naked eye. It's just this black film, which is good because we want it to absorb all the light. And so these are just some textures, or morphologies is a word that material scientists use all the time. And so that's what mine looks like so far. And so looking back, there's a lot of methods for cleaner energy. And if we can do a good job of producing these things, then we can essentially save the planet. We can fuel space travel. We can help our own environment. And so, yeah, definitely really important fields to get into. So that's my presentation. Maybe DV can field a few questions if we have time. Thank you.
Thank you. Thank you so much, Casey. We will have questions at the end, or we will encourage the participants. The maximum that we had was 91. If we can detect the mischief mongers, I'm sure we have at least 75 serious participants. So we are going to encourage them to send questions. Now, I'm going to introduce Mr. Kevin Yates. Over to you, Kevin. Ladies and gentlemen, I have pleasure in introducing Kevin to you. Dr. Kevin Yates recently earned his PhD in chemical engineering with the designated emphasis in biotechnology at the University of California, Davis. His research concerns the use of plants for production of recombinant therapeutic proteins in limited resource environments. That's really very interesting. Kevin goes on to say that as humankind makes progress towards becoming an interplanetary species, we must confront the vastness and remoteness of space beyond Earth's orbit. Long-term missions to the Moon, Mars, and other limited resource environments, what we call as LREs, will require improved strategies for life support, including manufacturing of food, pharmaceuticals, and materials via in situ resource utilization. We propose the use of biotechnology to meet these needs, as it offers numerous advantages over traditional abiotic solutions. Over to you, Kevin.
All right. Thank you so much for the introduction, and I'm really glad to be here and share of what I'm calling the biotic future of human space exploration. So we have an interplanetary future. We want to go beyond just Earth here. Now, some will argue that like robots do this very well. I've shared a couple of patches here for my missions I'm interested, which are JUICE and the James Webb Space Telescope. But humanity is ambitious. We realize that we do have our concerns here on Earth, but also we want to travel beyond. So I think the first step in this is NASA's Artemis program, which will involve a lunar base and a gateway that orbits the moon. But this isn't the only approach. Roscosmos and the Chinese National Space Agency also have plans for long duration crewed missions. And then, of course, India has the Gaganyaan, which will go up maybe in a couple years. So that's in development too. And over the weekend, I just read this article in Ars Technica titled "India, a Growing Space Power is Forging Closer Ties with NASA." So I think we kind of covered that earlier in this event, but certainly check it out and read it for a good overview. So some of the challenges that we're going to face in this interplanetary future, I mean, the first one I think of is distance. And by distance, what I really mean is time. It takes a long time to get humans or cargo anywhere because of the distances involved. And outside of low Earth orbit, we're affected by cosmic and solar radiation. So that really changes the sort of the effects that we might see on materials and things that we want to bring. And in microgravity and from this radiation, there are a lot of physiological effects on living things. So that's us humans and any sort of like biological material that we want to bring along. And then, of course, being that this is a limited resource environment, it just makes everything harder. You are confined to a spacecraft. You have these distances and times to deal with, and so on. So my research has concerned the use of biotechnology in space. There is a program within NASA called CUBES, the Center for the Utilization of Biological Engineering in Space. And so traditionally what we do for a mission is we just bring everything that you need, such as like on the International Space Station. But the problem with that is that mass is a significant constraint for any mission. So essentially, as a rule of thumb, what we say is that for every 1 kilogram of stuff that you want to bring, things you're going to use, you will need 99 kilograms of support. So that's increased volume, increased power and cooling requirements, and so on. Meanwhile, the space environment can degrade your supplies, especially things like medicine, and resupply is difficult for something like a mission to Mars or even to the moon. If it's degrading in space and it takes a while to get there, like how are you going to handle that? And then also, if everything's just prepackaged, what will you do with all the waste? The wrappers and the bottles and all of this. Are we just going to jettison it out into space? I don't think that's a good idea, right? So what we propose is the biotechnology solution where you make what you need. This includes food, chemicals, and materials. Everything is designed to be recycled. So a waste stream from one process becomes an input stream to another process. And that way you sort of close the loop. Also part of this is in situ resource utilization, where you use the things that you have available to you. And I'll expand upon that more in a future slide here. And then so people will ask, well, how do you compare this? How do you know which of these solutions is optimal? So we use something called equivalent system mass. And since I said, mass is so much of a constraint for space missions, we reduce everything to just this mass metric. We use this equation and all the variables aren't important right now, but what I need to point out is, so this involves the mass, volume, power, cooling, and crew time. And through this algorithm, we come up with a way to just say, okay, this equivalent system mass for this system can be compared to other systems with just one number. And that's since been extended, but it's kind of the sort of the classic approach that like NASA will use. So I think it's important to, since we're talking about education today, to give a little bit of context of who I am, where I come from. So I'm a non-traditional student, and I actually started out as a computer scientist. I decided I wanted to actually work more than I wanted to get that degree. So I worked in IT, and it was fine. It paid pretty well and all that, but I sort of felt that I was, confined to a box of sorts, right? So like the space in which I work is limited to, computer software and hardware that is designed by people. So I started to realize that what I really wanted to do is like the box I wanted to work in should be the size of the observable universe, or maybe larger, Um, and so I sort of quit that, and I traveled around a lot. I did a lot of different jobs. So I was like I say, I mostly worked in IT, but I worked in a steel or iron foundry. I cut grass, do construction, drive a truck, all while trying to find sort of what I wanted to do. And from this, I realized that I wanted to be an engineer. I wanted to be an engineer. So I decided to become a chemical engineer and go to Michigan Tech, way up here in a pretty remote part of the United States. And I got my bachelor's of science and chemical engineering. But near the end of that, I said, I think I want more than this. I think I want a lot more than this. So I decided to go to graduate school, and I ended up going to the University of California, Davis. And even when I got there, I was like, okay, I minored in electrical engineering and mathematical sciences. I don't know much about this biology stuff, but it just seemed like a really fascinating thing to approach. So I did it. And there's much more to this story, but maybe another time. So what I'd like to talk about is the discipline of space bioprocess engineering, sort of a discipline that's being formalized and formulated. And with this discipline, we want to ask, like, how do biotech solutions work together? And we see it if we decompose space bioprocess engineering, we see this idea of the intersection of biology, space science, and systems engineering. And so some of those disciplines, like we already know what they are, but just to go over them, biological engineering. So that's just synthetic biology, covered a lot of different things. Astronautics, mission design, and astronaut sustainability. Space science, so that's like, how does space itself work? That's important for all the rest of this stuff. And then astrobiology, how does biology work in space? And so one question, like the previous one with equivalent system mass, is how do we design and constrain solutions to meet performance goals? So as an example, I'm going to talk about space bioprocess engineering on Mars, for example, on the surface of Mars. So I mentioned in situ resource utilization. So these are things that we could find on Mars, like water and ice, atmospheric gases, regolith, sunlight, and then those feed into this process where we process them and get these things in a format that we can use. Those in turn go into processes like in situ manufacturing and food and pharmaceutical synthesis. And from that, we get food, medicine, fuel, materials, but also the waste streams from those processes can go back into some kind of loop closure process, in which case it feeds them right back into the other processes that we are using. So some examples of these things, like in situ resource utilization, would be carbon and nitrogen fixation, or enriching the regolith so we can grow things in it. In food and pharmaceuticals, we would make food, medicine, we would engineer microbiomes for the plants so that they can grow optimally. Microbial nutrition would be a part of that. Manufacturing of bioplastics and bioceramics. To close the loop, anaerobic digestion will be an important part of that. And then, we also have to consider systems design, so human health and performance. How are we going to keep people alive in these inhospitable environments? And the way we approach this is with a number of metrics here. So I'm just going to go through these real quick. Modularity, so everything should just drop in and work wherever you want to put it. Recyclability, like I said, we want to close the loop and reuse as much as we can, so we don't have to feed in new stuff to the process when we can just reuse what we have. Supportability, so that is, it has to work on Mars without requiring a constant resupply. Autonomy is an interesting one. It's obviously a hot topic right now. But we'd like for this system to be able to operate autonomously, with a minimal amount of human intervention, while still being resilient and functional. And lastly, sustainability. We have to think about what our environmental footprint is going to be, even on a place like Mars. And so with those metrics, we approach this by designing it in more of a classical sense. So we constrain it, pick our targets, design a workflow, design some kind of bioreactor to do it, design an organism for the bioreactor, implement it, test it, and then from that feedback, we go back to design until we develop something that meets what we were trying to do with our constraints and engineering targets. Now, we zoomed in to space bioprocess engineering, which I mentioned here, but we also have to consider how it fits into the greater, what we're calling kingdoms of life sciences in spacefaring. So we also have to consider bioastronautics, which is a study of effects of spaceflight on biological systems. And then one I think is really fascinating is astrobiology. So that's a study of the origin, evolution, distribution, and future of life in the universe. So big topics with big impacts. So how, as a practical example of this, consider the production of pharmaceuticals. So normally, right now, to make them, generally what you do is you have a bioreactor facility and you need production and support equipment. So you need bioreactors, pumps, tanks, chromatography equipment, all this stuff. You got to have sufficient and reliable power and utilities to keep it running, timely and reliable supply chains, lots of consumables like growth media, chemical reagents, single-use tools. And the whole time you have to keep this all sterile. There's the quality control is huge, and there's something we call current good manufacturing practice, which kind of sets the standards. So there's a lot of resources involved here. And in emerging economies, maybe they don't have reliable power and utilities or supply chains or whatever, but even just the capital and operating costs can make it infeasible to actually produce something like this. So as an alternative for something that we would use in space exploration, we could also use on Earth, consider that we treat whole plants as single-use renewable bioreactors. So here in this picture here, I'm showing some lettuce, transgenic lettuce, which is producing a bone regenerative hormone, which I'll talk about. It's just growing in the greenhouse like any other kind of lettuce plant. You could grow in the field, you could grow it in a growth chamber, whatever you want to do. And that is a huge advantage. I don't need a whole sterile bioreactor in here to make medicine. And as we've seen, in recent events, like it's better to make things domestically than depend on trying to import them, because you just don't know when that's going to get disrupted. So essentially what I'm trying to say here is that if something is good for spaceflight, it's also probably good for use on Earth in Earth-based low resource environments. So one thing that we've been talking about here in the United States is this manufacturing workforce of the future. So one program I'll highlight is called BioMade, which stands for Bio-Industrial Manufacturing and Design Ecosystem. And the goal of this program is to secure America's future through bioindustrial manufacturing, innovation, education, and collaboration. It's funded by the U.S. Department of Defense. And as we know here, if you want to get something funded, just make it a national security issue. But anyways, it would involve the production of chemicals, solvents, detergents, reagents, plastics, films, fabrics, polymers, and other things. And yeah, we want to do that here. So there's a big push for that. And like other programs like STEM Connector are like, okay, well, how are we going to build a biotech manufacturing workforce? We can't just say, oh, we'll just have people with PhDs or even bachelors of science do all the operation of the machines and such. We need like a certification program or something you can do with a two-year degree, where we can get people into this workforce and take into account political, economic, sociocultural, technological, environmental, and legal factors. So there's a lot of good reports on this. So if you look up STEM Connector and BioMade, you can go deeper into that. All right, as I promised, I will talk a little bit about my research. So one of the problems in space flight is that you are going to lose bone mineral density from being in microgravity. So on the left here, I show just a diagram of how bone is normally broken down by osteoclasts in the body. This is normal, and is rebuilt by osteoblasts. But the problem is that in microgravity, for a number of reasons. Osteoclasts are doing more work than the osteoblasts, and so desorption of bone outpaces formation in microgravity. So what that means is that maintaining bone health in space is pretty difficult. And maybe you're fine while you're flying, but landing is another thing. You've probably seen the photos of astronauts being carried out of the return capsule because they have trouble walking in gravity, and it can take them weeks or months to recover. So I'll direct your attention to this figure over here in the upper right. So over the course of a person's life, an average person is going to have this bone density where, it starts to maybe decline in middle age. But if we send a middle-aged astronaut to space and over the duration of a Mars mission, they might rapidly cross the threshold for osteoporosis. And that's really bad. It'd be really hard to fix a bone fracture in space or on Mars. And so people ask me, does exercise prevent that? No, it does not. Not on its own. And you can take medicine. I show a picture of an astronaut with bisphosphonates, which is how we currently deal with it, but you have to carry everything that you need. And as I said, carrying cargo is difficult. So what we propose is the use of a fusion protein consisting of human parathyroid hormone and the FC domain of a naturally occurring human antibody called IgG1. So that's this big part down here. And we attach it to the functional part of parathyroid hormone, which essentially results in bone formation. So right now it's currently a drug called Forteo, and it works. But when you attach it to this FC, you don't. We're hoping that you won't have to inject the PTH every day because the larger size will result in slower clearance, so it stays in your body longer. And anyone who's done like liquid chromatography is probably familiar that the FC domain can be used for purification because it has an affinity with protein A, which is like a real industry, very, very common in the industry. So that makes it easy to purify out of plants. Oh yeah, sorry, I should have mentioned, we propose to make this in plants, right? So just like I was showing before, you just grow the plants and they will make this. The FC can bind to FcRn receptors in your epithelial cells, so again, may increase bioavailability. We added a mutation here to keep plants from sticking sugars onto it as they like to do. That's the A-glycan mutation. We just don't want that creating any kind of immune response. It gets stored in the endoplasmic reticulum of the plant cell for stability. And this has been tested in animal rat model. So we do have transgenic lettuce, which is able to produce this. And again, I have to emphasize, you just grow it like normal lettuce. So my research was mentioned and sort of joked about on a late night talk show here, which Stephen Colbert says, you found a way to make food produce bone juice, but the food you choose to do it with is lettuce, and said that lettuce is boring. And yes, I have to agree with that. But the thing about lettuce is that the leaf is ready to use as soon as it reaches its desired size. So as soon as you see it, you could eat it, right? You don't have to wait for a fruit or a root, and you don't have to cook it. One plant can produce like 900 seeds or more. So, you grow one plant to make seeds, you can just keep producing this PTHFC. Food crops are going to be part of a long duration mission no matter what. So if we're already growing crops for food, we might as well grow them to make medicine. And then lettuce has been grown in low Earth orbit. And also, like, people like green growing things, they just like that, and it really helps keep track of time too in a place where there's or sunset. So they do consider like the psychological benefits. So the things I wanted to look at, a lot of numbers here, but really what's important is that I looked at how the amount of PTHFC in the plant changes over time to try to find the optimal harvest date, which looks like it's about 30 days after emergence, at which time the plant is producing on average across like the whole plant. We grind up the whole plant, 65 milligrams of PTHFC per kilogram of fresh weight of plant. And then I also looked at, I said, well, which is the best leaf? If you were just going to harvest one leaf, which would be the best one? So these results here are saying like, okay, maybe it's one of these older leaves. In this case, leaf number 2 has the most. And I think the amount of PTHFC has to do with like the growth dynamics of the leaf. There's a lot more to this, but I just wanted to cover that briefly. And just a couple more slides here. So we also model plant growth. We have the what's called the modified energy cascade, which is kind of like the standard model that NASA will use. And what I want to point out is that this model, it's time-based, but what it looks at is the photosynthetic photon flux density. So that's how much light the plant is getting, and the atmospheric concentration of CO2. And so those are the only two inputs for it, but it's a pretty good model and does match up with what we measure empirically. And so the cascade just takes into account the absorption of light, conversion of that to sugars, and then conversion of those to enzymes and structure in the plant. And the thing I want to point out is one of the outputs is crop biomass. That's important because, as I showed before, the amount of drug you get is just, you know, in milligrams per kilogram of crop biomass. And then we can use this model to predict how much biomass we're going to get given certain concentration of CO2 and photon flux density. And we can also look at the two effects on there. So it's a useful model. This is actually a schematic of how it works. I'm just going to skip this slide. We don't, but let's go to the next one. So when we combine those models with the empirical data, we can say something like, if an astronaut is going to eat the lettuce, which we hope will work, we're ways from testing that, and you have 10% bioavailability of that bone regenerative hormone, PTHFC, we calculate that an astronaut would probably need to eat 47 grams of lettuce per day, and that lettuce would take 152 square centimeters to grow. And then we could also sort of look at the number of doses you might get if you started with some number of seeds, you got some amount of biomass and had some fraction available. I mean, it's really just a linear combination, but it makes a pretty picture. So yeah, that's the sort of things we want to consider. So I want to thank Explore the Space and Professor Risbud and Ms. Brayfield for inviting me to this. I also want to thank the members of the McDonald-Nandi Lab at UC Davis, where I did this research. And the designated emphasis in biotechnology program at UC Davis was also really cool, really helped me out in thinking about biotech and industry. And then, of course, NASA and CUBES. And so, yeah, I want to say thank you all for listening, and thank you for the opportunity to present this.
Thank you. Thank you very much, Kevin. Dear participants, we'll take one question. In fact, we have a common question from a private university, both for Cassie as well as Kevin. Cassie and Kevin will be very happy if your answer to this. What is your experience when you talk to the US industry? I'm sure you would have approached the US industry by now. What is your experience when you talk to the US industry about your research? Can you share your experience when you take your research, or when you take your findings, when you go to the US industry? If you have done that, what is your experience?
Yes, I can answer that question. I actually worked in industry for 5 years in between my undergrad and starting my PhD. So I got a lot of experience in that world and what it takes to have like a large manufacturing factory, and the language you use when speaking to people in industry and about, you know, problems and plans in industry. And so industry and academia are definitely two different environments. And I think in industry, if they're interested in the work or the research or the methods, industry is where the money is going to be. And in academia, it's always asking for grant money, whether it's from a government or an industry. And so there's always that extra step of proving that the project is worth funding, which I know we've all dealt with.
Yeah, and I can add on to that. So, you know, biotech, especially here in the San Francisco Bay Area, you know, close to where UC Davis is huge there. There's so many startups and established companies, and so everybody who wants a piece of that is here. And so typically when I present my research, what people will ask is they'll say, how can I apply that to what I'm doing? So I find that with biotech, you know, when you have some kind of approach, it turns out that, you know, you can use it for a lot of different things. So if I say, yes, I can make this drug in lettuce. They'll say, oh, I wonder if you can make this other thing in lettuce, or maybe you can make your drug in another plant. So, because we have the central dogma of biology, which is that, we have DNA, which is transcribed to RNA and then translated into basically proteins, and that works with any living thing. So everybody's very aware of that and says, hey, how can I use this for whatever it is I'm doing?
Thank you. Thanks for that. Can I request a last word from Professor Subhash, please?
Yeah.
Please.
Yeah, I'm delighted to hear all of the talks today. I mean, Cassie and Kevin, of course, have done a great job, as I would have expected. And also thank you, DB and Tim, for building this whole apparatus that has now come to fruition in meeting today. And we hope to look forward to more, internships and opportunities like that. So let's stay in touch to do that. So any of the students that are listening in today from India or in the US, if you'd like to contact me, I can also put you in touch with our director of my successor at the Internship and Career Center, Marcy Kirk-Holland, who will also advise you, because in my time there for the 9 years I was at the ICC, we placed over 6,000 interns worldwide in everything from semiconductors to manufacturing to Oaxaca, Mexico, to France, wineries, everywhere. So I think the Internship and Career Center is a very underutilized facility at Davis, and both international and domestic students are encouraged to do that. So that's an angle I would like to pursue as we talk about short certificate courses and things like that. The ICC used to teach a course when I was there that I started called What in the World Should I Do? That was the title of the course. And I see Tim smiling because he has found his way of what in the world he should do, right? And so we are encouraging people to kind of use the ICC and the Career Center and the career fairs we have here, and everybody here, including international students, participates in it. So that's a dimension I think we should keep in mind as we build this approach. And thank you for organizing everything today.
Thank you. Thank you, Professor Risbah.
Do so.
Sure. Can I request Tim for your inputs, please?
Yeah, I just want to say, I think Subhash or Professor Risbah had said this, is it's really important to have your passion determine your direction. So what you're passionate about is what you should, that gives you the compass, needle in the compass that you can then focus on your direction. And it could be in many ways. And maybe it's not obvious in the beginning of your career, and you've seen here from a variety of people that things change. But remember, life is a journey, and have your passion help you understand your purpose. And then collaboration is so important. You can't do it by ourselves. You really have to work with others in other countries and other cultures and other skills and disciplines to be successful. And space is a great objective where we can all get together. It's not political, as I say, it's really something that we all share in common, passion to explore, develop ourselves, make the human civilization better. Again, collaboration is so key. So again, thanks, DV, for creating this platform for collaboration. Phenomenal work. Congratulations. Thank you.
Thank you, Tim. Ladies and gentlemen, we have Dr. Jaydeep there. Jaydeep, is it okay if I request you for a few words, please? Dr. Jaydeep Mukherjee from NASA, FSGC. Dr. Jaydeep, please. Is it okay if I ask for a few words from you, please? Dr. Jaydeep?
I think he has to unmute. Yeah, he's muted. Jaydeep, you have to unmute. Now.
Yeah, no. So it was not allowing me. Sorry. Not great presentations by both Kevin and Cassie. Kevin, I wanted to let you know that your research will be interested. There's a group at the Florida Institute of Technology, and there's a group at MD. They would be interested in your work. Also at Kennedy Space Center, there's a group of doctors. And of course, the veggie is at at Kennedy Space Center. So you might want to contact them. And Cassie, I loved your presentation, especially when you're talking about, generating energy, especially when we're going to the moon, going to the south pole of the moon, you're going to have concerns because most of the ice that we find are on the floor of the craters. And how the heck can we harness the solar energy to take the rovers down to the craters, bring the ice up to the surface, because no sunlight reaches down. So I think the work that you're doing would be interested. I also wanted to address the question that the couple of you had about how industry and academia work together. So NASA has two programs called SBBR and STTR. And what they do is they connect universities with industry. And the reason I say that is that when university works with industry, the people doing the research work are the students who are doing the actual work. And I know a lot of cases where students have started their own companies as a result of this work. I have a program in Florida where I get potential topics of commercialization from Kennedy Space Center, and I distribute to all my Florida universities, and I fund them to do some projects where they hire the students to do the work. And then these students then become entrepreneurs and start companies. So to all the students out here, you are at such a great time to be in this domain of space. And on Friday, India is launching Chandrayaan-3, and the idea is to again launch a lander rover at the south pole of the moon. So great time. Also, I'll be glad to answer any questions via email. There's a lot of possibilities for everyone, but great presentations for everyone, including Tim. I love Tim's presentation because his story will be very similar to a lot of people in India. When I was growing up, I wanted to do astronomy, but everyone said, don't do it. Either be an engineer or a doctor or an accountant. But now the possibilities are endless, even in India. So great job. This is an amazing program that I listened to right from word go.
Thank you. Thank you so much, Jaydeep. Dear participants, there are about 6 questions, 4 to Kevin and 2 to Casey, but I'm going to send those questions to Kevin and Casey by email, and we are going to encourage more questions in order to make sure that the program ends on a very, very good note. I'm going to close this program. Our sincere thanks to Dr. Kiran Kumar, former chairman ISRO, Mr. Tim Dyer, Professor Subhash Risgood, Cassie and Kevin, and a special thanks to Dr. Jaydeep. We also see Mr. Balagurunathan, a great mentor for our programs, who's also participating. A big thanks to all of you. Kindly watch out for more information. We are currently talking to companies, a few companies in India, a few companies in the US, and to a few government agencies, both in India and in the US, on taking this program forward. We welcome your suggestions and participation. Thank you so much, everyone. And a very, very good morning again to the United States of America, and good evening to friends, and good night to friends in India. Thank you and goodbye.
Thank you, Kevin. And bye, everyone.
Thank you, everybody.
Thank you, everybody. Thank you.
Thank you. Thank you. Thank you. Thank you.